Okay, hello everyone. I wanted to do a couple of different things today, and I'm trying to make sure that my software is working correctly. I haven't tried to present and share a video before, so hopefully this all runs smoothly today. So what we're going to do, we've got two slide decks. We're going to go through the stereotype threat and resilience, and that won't take too long except for the two videos we're going to watch together, and then we'll go through the slides on computational geometry. So the first thing in here is stereotype threat. It says it refers to being at risk or confirming negative stereotypes. And so the idea of this is that people feel like they might be a stereotype, and that internally, even if subconsciously, they might reaffirm those stereotypes that exist in society and cause it to be true even though it might not be true. Okay, so I'm going to try to switch my source over here to the video, and then we'll start this one.
My mom was also a mathematician, and I grew up with the term stereotype like casually thrown around the household. But there's some pretty legitimate research showing that if you think you're going to be less good at something, you'll start being less good at it.
There are all kinds of forms of stereotypes, because there's negative stereotypes about almost every single identity we have, our age, our race, our religion. But if you're, say, for example, a woman trying to succeed in advanced computer science courses at an old university, the prospect of being seen in terms of the negative stereotype about women's math ability can sort of knock you sideways. We got men and women who were very, very good at math. And we brought them into the laboratory and we gave them a very difficult math test that we knew would cause frustration. Our idea was that for these students, the situation would become different for men than it was for women. For men, they'd be frustrated and worried that they weren't performing as well as they might have anticipated. But for women, in addition to that, they might have worried that they're maybe confirming that alleged limitation in math ability that stereotypes in our society attribute to them. That extra word would use up an extra amount of bandwidth as they fight with that and resolve to push through that and to disprove that and all the things that we do. For women performed a full standard deviation worse than men on a test, even though we had carefully matched the men and women for having the same skill level when they began. We do the experiment over again, but this time we tell them, look, you may have heard that women don't do as well as men on difficult standardized math tests. But that's not true for the test you're taking today. The test you're taking today, women always do as well as men. They always have. They always will. Under that simple instruction, women's math performance went up to match that of equally skilled men.
Even though women may do well in many of these subjects in school, there's this idea that you have to be a genius or have a certain kind of mind to succeed in that as a field. Women who have this view that it's only a fixed kind of person who belongs there start feeling the stereotype more strongly. They don't choose a field that says it's sheer brain power that can't be taught. Some people have it, some don't, because they know who the field thinks doesn't have it.
Okay, so the thing that we want to remember here is that, first of all, the associations are ideas from society that don't necessarily have any basis in reality, and that you're all students who have made it to U of M. There's a reason you're here. So being aware of these situations is part of the solution. Knowing that the problem can exist makes it better for us to both reduce its effects on ourselves and to be understanding of other people and not propagating these stereotypes that have no basis in reality. So consequences of this, as they said in the video, people might not study something that they want to study, or that They may do less well in it because of the cognitive time spent thinking about this assessment of not them as a person, but them as some group of them, whoever them is. So it causes this cognitive load and emotional load that takes its toll. So one of the things that you, like I said earlier, is affirm yourself, affirm your self-worth. You know you're a good student. You know you made it into U of M for a reason. You know that your hard work is paying off. You can see it in your outcomes. You can see it in your projects. So think about your future self. Where do you want to end up, and what do you have to do to get there? Now, looking at role models is something that we try to do in 281. We try to have good role models in our staff. We try to get a good variety of staff members so that hopefully there's someone on staff that any one of you can identify with. And there's a couple of people here, some of whom I know off the top of my head. Katie Bowman was a U of M student who went on to graduate school somewhere else. I want to say MIT or Carnegie Mellon, somewhere like that. And she wrote the software that stitched together all of the data that made the first black hole image. Alan Turing, who's a tragic figure. If you haven't seen the story of his life, I highly recommend it. Alan Turing is a personal hero of mine because although I don't have the same issues that he had, I understand what he had to overcome. And just as an aside, there's a Raj Reddy, a Turing winner there. U of M has more Turing Award winners as alumni than it takes the next 3 schools combined to have more than we do. So we have more than number 2 and number 3 put together. It takes number 4 added to 2 and 3 to overcome the number of Turing Award winners that U of M has produced in alumni. Dorothy Vaughan, if you haven't seen the movie about the Hidden Figures, great movie also. Okay, we have another video on resilience, and I'm going to switch over and get this started, and I'm going to chase a cat off of the counter here in real life.
I didn't get an A in Chem 35. I didn't get a B in Chem 35.
I didn't feel like I belonged at Stanford University as a faculty member for about 9 years, and I've been here for 9 years.
I didn't get my first article published. As a law professor at Stanford,
I didn't stay in Physics 61. I didn't finish the second problem set. I just dropped the class.
I didn't pursue my dream of becoming a math professor because I screwed up and got a C+ in freshman calculus.
I didn't find my passion through my major.
I didn't get my advisor to accept a single paper of mine without making me rewrite it entirely from scratch.
I didn't succeed at saving my sister.
I've never received a fellowship or award in my field.
I didn't study engineering as an undergraduate or a graduate student.
I didn't pass half my classes the first semester of freshman year. This is not a good thing.
I did decide that I was already equipped with everything I needed to be here. I didn't have to be a Stanford professor in the mold that I thought. I had to just be myself.
I did get a C in Chem 35.
I did expand my faculty network, learned a lot more about the submission process, resubmitted much more broadly, and my article was accepted.
I did go to medical school and become a physician, and I'm glad that I did.
I did teach Physics 61 after I became a professor, and I think my experience helps me to be a better teacher.
I did learn how to become the biggest critic of my own work and how to think and write more clearly. I did figure out that I hadn't passed them not because I couldn't, but because they just weren't things I cared enough about to go after. and I realized it was time for me to go look at some things I care more about. When I did that, I got happier and a lot more successful.
I did find my passion through electives that connected to my major in ways I never could have predicted.
I did apply for this faculty position at Stanford University, even though I wasn't qualified on paper.
I found validation and self-worth from people I respect who value my work.
I did learn to enjoy the people in my life, to love them, and to be grateful for the time that I do have with them.
Okay, so I have one for you. I didn't pass freshman chemistry 2 the first time I took it at Michigan Tech when I was an undergrad. On the first 3 quizzes, I got a D, an F, and a worse F. And I dropped the class. And I retook it later and got an A in it. And I realized after I dropped it, part of the reason why was I was taking too many credits, too many semesters in a row. Actually, we were on a quarter system. So I had taken 18 credits, 17 credits, and I was just wearing myself down. It wasn't that I couldn't handle the class, it was that I couldn't handle the pace that I was trying to set for myself. One change that occurs sometimes when students come to U of M, oh, you can hear it, but you can't see it. Okay, I'm sorry about that. I didn't see that because I've got my tablet here. My laptop has only one screen, so I can't display everything I want at the same time. But we do have the links to those videos, so I guess you'll have to go watch the videos if you want to see the images. It's probably a copyright issue at some point. There's probably a digital signature in there that's not allowing it to be re-recorded, possibly. So at least we got to listen to it, which was the important part. Anyway, like I started to say, when you transition from being, say, the best student in your high school to one of many students at U of M who were the best students, you have a bit of a transition there. And so you just have to remember that you do have the skills to be here. And when you get to U of M, you tend to be one of the many fish who are all great students. So failure happens to all of us, and we have to deal with it at some point. And the feelings that come with it, the frustration, the sense of worth decrease that you might feel, that comes with it, but we can understand that and better be ready for it. When companies go to look at your transcript, having one class, even within your major, that is lower than all of the others, is not something that's going to keep you from getting a job. They do dislike seeing a trend of getting a D and then retaking it and getting a C, getting a C minus, retaking it and getting a C plus, taking it and getting a D plus, retaking it and getting a C. They dislike seeing that trend over and over, that you have to do something twice to succeed. But if one class, even within your major, is lower than you would like, it's still a reasonable thing to see on a transcript because it happens to lots of students. So the resilience part of this is getting past those failures and moving on and succeeding in the future. And true growth comes through difficulty and adversity and overcoming it. So the 3 things that it can take a toll on is the emotional impact, and keeping a positive attitude for yourself and avoiding comparing yourselves to others can help. The mental aspect of the distraction of thinking about these things, and setting more reasonable expectations on yourself, persevering, learning how to study, learning how to break up your time so that you work for a while, take a break, come back to it can help. And overall physical health can help with both of these. If you're not getting enough sleep, it's hard to deal with everything. So there's a bunch of different resources here that you can look at that are available through the university. Okay, and you've got this set of slides, you've got all the links for the videos, etc. Okay, so now we're going to talk about computational geometry. And we'll see if that looks right. No, it doesn't quite look right. Let's see. Change, rotate, and restart, and hopefully it'll look fine after this. Okay, that looks better. Okay, so computational geometry, I'm going to tell you up front, this particular slide deck makes a bad set of exam questions, meaning there tend to be very few exam questions off of this. When we try to create them, they tend to be too hard, in which case we eliminate them, or too easy, in which case sometimes we keep them because you deserve to have some questions on the exam that are fairly easy. So I can say definitely there will not be any hard questions on the exam from this. There might be an easy one, and we'll go through this. There's a lot of cool stuff in here. So it's going to seem a little bit disjoint, all the different topics we're going to talk about. So when we look at images, on a screen, down at the tiny level, there are pixels, and each pixel is actually represented by multiple colors combining to make that particular color appear in that pixel. And so the higher resolution we have, the more range of colors and brightness levels that we allow can produce a large difference in the recording size and the image size, video size, etc. If we look at vectorized graphics compared to pixelized graphics, when we take a small pixel image and we blow it up, we see the pixelization, that limited resolution. Vector images, on the other hand, are created with a description, and that's how modern fonts work. If you see things like TrueType fonts contain a description of how to form the character, and then that character can be generated at any font size, looked at with any resolution, and we still get a good looking font. Whereas if we look at a bitmap and blow it up, it becomes much harder to read. When we look at image compression, so years ago, and I know there's disagreement on pronouncing this, GIF, G-I-F or GIF. So the original people say it's GIF. I've pronounced it GIF forever. Anyway, originally those images were a direct translation of the picture. Then when the Joint Picture Group, the JPG group, started trying to reduce the amount of size required by an image, which would make it possible to transmit bigger images with less bandwidth, they looked at how they could remove some of the information but still have the visual cortex processing fill those details back in. And so if we look at, say, the first two images here, the original size image and the 85% compressed image, those look very similar to the human eye. And then if we increase the compression, we can see the difference. So beyond a certain point, your brain stops fixing details. And if we look at how graphics are produced on a computer, we can produce, like in Paint, when we draw a line, it's turned into pixels. And if we zoom in on it, we can see the pixelization as we zoom in further and further, whereas more advanced computer-aided design packages do vector graphics and store them in a format that describes the shape so that it can be then rendered on the screen at any resolution. So with those big ideas in mind, let's look at some smaller ideas. So when we start to look at points and line segments and lines in different dimensionalities, so if we have 2 dimensions, we can represent a point, xy coordinates. We can represent a line segment as the 2 endpoints, say. We could represent a line, not a segment of a line, but an entire line, given some things like a slope and an intercept. And if we had 2 different points, there's a way to calculate some values that could then be used to compute our slope and intercept. When we do this, we want to use, I would say, doubles. Until it's time to draw it, keep things as doubles because they have more precision. Double variables tend to have approximately 15 decimal digits of precision. It depends, we're talking base 2 representation changed to base 10. So it's approximately 15 decimal digits of precision in a float, about 7 decimal digits of, 15 in a double, 7 decimal digits of precision in a float. So if we want good calculations, we carry out everything on doubles until we're done. When we look at collections of points, points can then become something like an image. Points can then become a polygon. We could have a representation of Michigan that has, say, a description of the border of Michigan and then fill it using pixels. If we look at different ways to store things, we could have a 3-dimensional mesh, which is shown here with the 3 different heads. We can have a 3-dimensional mesh at different levels of resolution, and that's how we store things behind the scenes. Then when we render them on the screen, we must turn them into those pixels. Now we can do transformations, and this is something definitely not going to be on the exam because this depends on linear algebra 214. But if we want to transition back and forth between xy coordinates and we want to do a rotation on it, we actually do the rotation using sine, cosine, and some linear algebra here to multiply our x and y by a matrix of sines and cosines of the angles we want to do a rotation about a point given an angular rotation. And actually we can do this in 3 dimensions also. And I've actually seen from like 1985-ish, there was one of the first really good 3D games was called Elite. And Elite was a space flying game that existed on lots of different computers. It existed for like the old Apple IIs, Commodore 64s, some British computers, I think like the Acorn, and it did, I saw like the developers' handwritten notes of it once, and they had the 3D version of this written out, was how they did the rotations of the spaceship in the 3D simulation. Higher level example of this is doing design for, say, a car company where they modeled the design in CAD software. Now let's look at some basic questions. So if I've got 2 lines, we want to know, do they intersect? Well, they're either parallel or they intersect. So if they intersect, find their point. If I gave you 3 points, do they all lie on the same line or not? If they don't all lie on the same line, if they don't all lie on the same line, then there must be a triangle associated with those 3 points. If there's a triangle, then the triangle must have an area. And another question, are those points ordered? So if I give you like 0.1, comma, 0.2, comma, 0.3, if I list them, do they look like this? P1, P2, P3. They describe a triangle. I've listed them in clockwise order. Could you determine, given three sets of xy coordinates, could you determine whether they represent a clockwise triangle or a counterclockwise triangle? If I gave you a point and a line, is the point on the line? If it's not, can you find the point on the line that's closest to the given point? If I give you a bunch of points, so I give you n points, one-dimensional, two-dimensional, three-dimensional, can you find a bounding box on those points? Can you find the pair of points that are closest to each other? Could you find, if I gave you a point that's not in the set, could you find the point in the set closest to the given point? So some of these we're going to come back and talk about ways to solve them, some we're not. So we're going to see a lot of questions. They generally fall into two different types. Are we dealing with a finite set of them, or I shouldn't say finite, are we dealing with a fixed number in our set, like 2 or 3 points at a time, or are we doing a collection of n of them? When we have just several points, 2 or 3 points, or line segments, usually we can fall back on some basic geometry and trigonometry and solve some equations. When we're dealing with a collection, we're going to have to deal with these simpler formulas many times, and if we do that, then we want to find the best way to do this. Can we do this in O of n squared time? Can we do it in O of n log n time? Could we do it in O of n average case time? Which one of these does it fit into? How can we solve it? Once we know we have to do this, apply these algorithms multiple times, what's the most efficient way to solve it? Okay, so first question here. If I've got 2 lines, first of all, we need to find out if they're parallel or not. So let's find the general form where we've got this slope and intercept. A and C are the slope, B and D are the intercept. So if the slopes are the same, if A and C are the same, the lines are parallel and they don't intersect. A case that I didn't mention earlier. If the lines are parallel but the same line, then they intersect everywhere. If the lines have the same slope but they do not have the same y-intercept, then they have no intersection at all. So when I listed them off earlier, I said basically either they intersect in one point or they don't intersect at all. Here we see I missed a case. I missed the point where they are the same line and they intersect everywhere. And if that's true, if it is the case that they are the same line, they intersect everywhere, if they have the same slope, otherwise they have no intersection, otherwise we've got a formula that we can use to calculate where is that point that they share in common. Now, what if I had 2 lines given by points? So if we gave you the slope and intercept, that would be easy. If I gave you points, then we've got to turn the points into a slope and intercept, and then we combine those into this huge formula here. So basically what we did was we went and took the x1, y1, x2, y2, and found the slope for this line, and we found the y-intercept for that line. We did the same for this one, and then we took those formulas, plugged them into this one right here, and it gave us this monstrosity. So like I said, we're not going to ask you hard questions about this on the exam. So you're not going to have to do things like rederive these or write all of these down. But you can see how the simpler formulas get built up into the more complex ones. All right, what about if we've got 3 points? We want to know, do they lie on the same line? So if I could check just 2 of the sets, so if I take P1 versus P2, P2 versus P3, if P1, P2 are both on the same line and P2, P3 are both on the same line, then we're getting closer to knowing if they are all on the same line. One thing we have to be careful of here is, depending on how we do our calculations, the order of calculations and the exact points that we're given might cause our mathematics to fail because they aren't necessarily equal, but they're very close. So there's an example here of, would I consider 0.999999 to be the same as 1.0? Probably. Would I consider the second one the same? Maybe. The third one, probably not. It's pretty obvious they're not. So what we can do is, when we want to do these tests, is instead of checking for equality, is A equal to B, what we do is we calculate the FABS. This is the floating point. My writing is terrible today. The floating point absolute value. So I take subtract the 2 A and B, take the absolute value of that, and if it's less than some limit which we choose, then we would say, I consider them to be the same. So we can set epsilon as long as epsilon is within the limits of the type we're using. Like I said, with a float, we would not want to make this more than like 6 zeros followed by a 1. That would be 7 decimal digits of precision. We don't want to go too far beyond that. And there's actually, you can ask the numeric limits library on the STL. There's actually a way to ask it for a certain type, what is the smallest possible distance between 2 values? So we could use something like, hey, what's the smallest possible value between 2 values? If it's more than, if it's less than 10 times the smallest possible limit, I would consider it close enough. Or we could just use whatever we think is appropriate for the data that we're working on. So we can also get rid of the absolute value and just do the comparison directly without calling the ABS function if we want to do like a less than or greater than. So if I want to know is A less than B, I can check if like A is less than B plus epsilon. That would be, hey, it's close enough. Okay, so back to one of the other questions that we thought of is the triangles. So if I've already determined, doing the pairwise comparisons, these points are not all on the same line, then can I determine clockwise or counterclockwise order? Now, with the formula here, again, if you've had linear algebra, what we're doing here is we're taking the 3x3 matrix determinant. If not, you can just follow the formula. So you just take the formula that's laid out over here, and then if that formula actually provides us with the area of the triangle. And if the area of the triangle comes out negative, well, that doesn't mean the triangle has a negative area. It just means that you went in a clockwise direction. So if the area of the triangle comes out positive, so if it's positive 5.3, we'd say the area is 5.3, and the points are listed in counterclockwise order. And if it was negative 5.3, we would say, well, the area is 5.3, but you listed the points to me in clockwise order. Now, what about if we want the area of a polygon? If we've got a square or a triangle, those are easier things to do. We're used to them. Well, how about some polygonal figure that's not regular? So that makes it a lot more difficult. If we've got a bunch of polygons, so we give a bunch of coordinates, and it says here, no segments are allowed to intersect. What that means is that the segments must touch only at their endpoints. We're not allowed to have a crossing because that would make it harder. So, for instance, I would say that figure is not allowed because it has a crossing. So we could simplify that. We would have to do it by hand. We would have to say, hey, let's simplify this into, whoops, my line is off a little bit there. We can simplify it. Let's cut this into two separate regions. Let's do each polygon separately. So the method that we're going to outline, this is not allowed. We can't have a crossing in the middle. But we could, if there is a crossing, we could separate it into two figures and do this method on each of those two figures. All right, so let's look at how we would solve the area of this polygon. It's a pentagon, but it's not regular, which makes it harder. And I've numbered the points here, 0, 0.1, 0.2, 0.3, 0.4. So that's the order they were given to us in. So there's the points that were given. We want to know what's the area of that polygon. Well, what we could do is we could draw vertical lines from every point. Let's draw a vertical line down to the x-axis. So now we've broken it down into regions. Now what we can do is we can look at the area of each region, which are now trapezoids. We know the formula for a trapezoid. We could find the areas of these trapezoids individually. We got a formula for that. That's easy. And there's a formula for if it's got right angles at the bottom. So what we're going to do for our more complicated figure is we're going to calculate the green area, the everything going down to the x-axis, including the figure we want and some stuff on the bottom that we don't want. Then, if we can figure out the area of the stuff we don't want, we can subtract. So we take the area of the green one minus the area of the red one, and we get the area we do want. So how can we manage that? Well, every one of these trapezoids has a top edge in the polygon. We just need to know, is this edge in the polygon, is it an edge of the green one, or is it an edge of the red one? Excuse me just a second, I'm going to drink the water here. Okay, so what we need to do is we need to find out for every one of those 5 edges in the original polygon, is it part of the top surface or is it part of the bottom surface? So that's what we got to do. We got to tell if an edge is red or green. Is it an edge of the green one or an edge of the red one? Now, if we look at our trapezoids, green trapezoids, when we have the xi, so xi is talking about the x coordinate in of these 2 points. So if I've got like x sub I is less than x sub I plus 1. So like when I'm going from point 0 to point 1, my x increases. If my x is increasing, that means it's part of the top surface. And from point 4 to point 0, remember we got to go all the way around. So I've got 5 points. I can't just consider 0 to 1, 1 to 2, 2 to 3, 3 to 4. I also have to go back from 4 to 0. This is kind of familiar to you if you've been working on Project 4, Part B or C. So the green trapezoids are going to have xi less than xi plus 1. Red trapezoids are going to have x sub I greater than x sub I plus 1. Now, when we plug these in, we see we've got really similar formulas except for when we do the subtraction. So the only part that differs here is these parts right there are going to produce a different sign depending on which order we do it in. So now what we can notice is that since we want the green ones to be positive and we want the red ones to be negative, we can simplify things and we always use the signed area. If the area of the trapezoid comes out negative, it gets subtracted automatically. This is related to when we were trying to determine if the 3 points go clockwise or counterclockwise. Same idea here. So if I take the area of each of those 5 polygons, I just add up their signed areas. The red ones will come out negative, the green ones will come out positive, and we're left with the yellow area. Now, there's the general formula for this follows the what's called the shoelace formula. We're going to look at what shoelace means in just a second. So the points, so it lists our points, and it lists here, so it gives us x0, y0 through xn minus 1, yn minus 1. These are the ones that are listed. We create an xn, yn that's equal to x0, y0 to make that wraparound really convenient so that we don't have to have a special case for it. So when we want to compute the area of the polygon, something that seemed really complex to begin with this odd-shaped polygon, actually comes out to be fairly efficient. It's linear time in the number of points. So even a figure that looks hugely complicated, we can find the area of it in linear time. Now we limited ourselves. We said back at the beginning we weren't going to allow crossings. One thing we did was when we drew it, we made a simplification without saying it. We made a polygon that was completely convex. What if we have a polygon where the regions, where it can double back and we can have a concave region? So for instance, right here, we would say, hey, relative to the outer figure, this section here is kind of concave, it dents inward. Well, when we have a more complex figure here, what will happen is the different regions will get calculated a different number of times. So if we look at over here in the green one, we compute a polygon here between these 2 points. Let's look at that one and that one. We compute the polygon under that one, goes all the way down, but that includes a region that's outside of it, but it also includes a region that's inside of it. Other parts of the formula will take care of it. So when we apply this, even if the polygon has concave regions to it, the math takes care of the double counted regions. If they get added in twice, they get subtracted twice. So you can see there in the multiple slides the double counting region down here at the bottom. This region down here gets included once for the upper region, this sign segment. It gets included again for that region. It gets included twice, but it also gets subtracted twice, and so it comes out even. The region inside of there only gets added once. A region inside completely gets added twice, but it gets subtracted only once, and it comes out. So all of the possible ways that those could work out get taken care of in this simple formula. So everything cancels out the way we want it, as long as we don't have crossings. Crossings mess things up. So we had this formula, the Shoelace formula. It refers to basically how they get computed. So this is a visualization of how that Shoelace formula works out. And granted, this one is slightly different from ours because it has subscripts are 1 based instead of 0 based. Same idea though. Okay, back to our line segments. So back to one of our other questions. So if I give you 2 line segments, do they intersect? And if the 2 line segments intersect, how do they intersect? Do they intersect like this, where they intersect at a point in the middle of both of them? Do they intersect like this, where they meet at one midpoint and one end point? There's actually a third one. Do they intersect like this? That's pretty easy to detect. Do they share one common endpoint? We're looking at in the diagram, it has the harder ones. So it's got the harder ones of do they intersect somewhere in the middle of one of the segments, or both of them are harder ones. Do they intersect at endpoints of both is pretty easy. Well, what we could do is we could try to project through there, through the bottom one. What if we project upward to there, and if we find the point of intersection of the line segments, or sorry, of the lines, find the intersection of the lines, is that point within the line segment? So we find the 2 lines formed by the line segments, then we check for the parallel, etc., like we did before, and then we check the intersecting point. Then we just check, once we've got the intersecting point of the lines, which we already know how to do that, once we have the intersection point of the lines, then we can just do simple x and y tests. Does it fall within the x and y coordinates for both segments? So if we go back here, we would find that, hey, when I project, if we look at the lines, hey, the intersection point is here, and that is within, so the x and y of this point is between P2 and Q2's x coordinates. Its y coordinate is within the y coordinates. When we perform the same test for P1 and Q1, both of them fail. It is outside of the x coordinates of Q1 and P1. It's outside the y coordinates of P1 and Q1. So either test there tells us it's not within there. So we already know how to find the intersecting point of 2 lines. Then we just have to do some simple checks against x and y to see if it's within each line segment. Okay, here's another one. This one's fun. We want to know if we've got a polygon and we've got some point, is that point inside the polygon or not? I'll give you a simple example how this comes up all the time. You're playing a first-person shooter. Someone shoots at you, and you think, hey, that bullet didn't hit me. Did they mess up their calculations somehow? You know, that went right between my arm and my body. I don't think that actually hit me. Well, here's how we look at doing that. So we've got our example where it might be outside, and there's the outside example. It could be outside in different ways. It could be completely outside the figure, like way over here. I'm going to put it way up there. It's not even within the x and y range of that polygon at all. That's fairly easy. The bottom one that I added here is within the x and y, but it happens to be outside. This one is more complex. It's within the xy multiple ways, but it's still outside. So we want to determine, is this point inside the polygon? Okay, what we can do is we can draw the parallel lines for a bunch of different circumstances. So these are for points A, B, C, D, E, F, G, etc. Those are all points. We want to know, is this one inside or outside? So we take point A and we draw a horizontal line through A and look at how many times does that line cross our polygon. Okay, A crosses our polygon 0 times. B, let's check B. So B crosses the polygon 1, 2, 3, 4 times. Point C crosses it 1, 2, 3 times. So we're going to go, actually I said line. We're going to extend the line all the way in one direction. We're not going to extend it in both directions. We extend it all the way in one direction. We count this one, hey, crossed 3 times. D crossed it. Ooh, D's problematic. D looks like it crossed it 3 times, but it actually intersected one of the points. E intersected 1 time. F intersected 2 times. G intersected 2 times. Okay, now for some of these it's easy. If the number is 0, definitely not inside the figure. For the 4, definitely not inside the figure. F that's 2, so this is not inside, not inside. The F that's a count of 2 is definitely not inside. However, G has a count of 2, but it happens to touch them both at the endpoints. D touches 3 of them, but at 2 of them at the endpoints. 1 definitely inside odd number, 3 definitely inside odd number. So this test gets a little problematic when we encounter an endpoint of the polygon. Then our numbers become problematic because G, we've got a 2 that's outside. D, we've got a 3 that's inside. One thing we can do here, okay, so if it crosses an even number of segments, it's outside, crosses an odd number, it's inside. What we can do is we can do this comparison with epsilon. Let's do our comparisons if we wiggle the point up and down a little bit. If we wiggle the points up and down by an epsilon, and check the number of intersections. If I go up a little and down a little, if up a little is odd and down a little is odd, those agree on the oddness. If I wiggle it up and down and they're both even, aha, they're both even, they agree on the evenness. Yes, your question, that's true. So the trapezoid formula works for even concave shapes as long as the shape does not cross itself. If the shape crosses itself, the formula is out. We would have to separate it into 2 regions that are not self-crossing and do it separately. Okay, so when we want to do our comparisons for the intersections, we can do it the way we described, doing with the horizontal line segments, but we're going to have to wiggle the points up and down when it crosses a vertex to decide if, since it crossed a vertex, is it really inside or outside? Okay, distance from a point to a line, there's a formula for that. We can look it up. Yep. Now, here's a different one. Suppose I've got a bunch of points and I want to draw the bounding box for those points. So I've got a bunch of blue points and we've got a hard example here in 3 dimensions. We'll back this off a little bit to 2 dimensions to work on it. So in 3 dimensions, I've got a bunch of points and I want to draw a bounding box around them. Well, let's bring this bounding box here. The bounding box actually gets pretty easy if we stay parallel to the axes. If I want to stay parallel to the axes, all I have to do, this is some of the things you might learn in 442. 442 is going to go on to harder problems than this, though, like do 2 objects intersect. But if you want to know if 2 objects intersect, we want to know if the line segments intersect. So the bounding box, if I want to keep the points, if I force it to stay parallel to the x and y axis, that's pretty easy. I just find the biggest x, the biggest y, smallest x, smallest y, draw a box. So if I were to take these points and I say, okay, highest point, you draw a line, lowest point, draw a line, rightmost point, draw a line, leftmost point, draw a line, I've got a rectangle around them. If we don't keep it parallel, and if we do that, this is O of n time. I just go over all of the points, find the biggest x, biggest y, smallest x, smallest y. There we go, I've got a bounding box in O of n time. If we allow the box, as in the diagram, if we allow the box to rotate, and it doesn't have to be parallel to the axes, we might get a bounding box with a slightly smaller area. It's a harder problem to answer. It is doable in O of n time, but you got to be really clever about how you do it. And it gives a sort of example here. In here, we try to figure out basically the biggest difference and the smallest difference in x and y to find out where the outer points will lie. Oops, drawing on it instead of flipping pages. Now, one of the nice things about this is when we're doing this, we can actually be even more computationally efficient when I want to do minimum and maximum. If I go through n things and I want to find the minimum, I have to do n minus 1 comparisons. I say, okay, x sub 0, that is the smallest I've seen so far. Then let's compare it to x sub 1, x sub 2, x sub 3. And then if I want a maximum of those points, I do the whole thing over again, and it takes me 2 times n minus 1 to do both. So if I want to do both, it takes me 2 times n minus 1. However, what we can do also is we can run through them once, and what we'll do is for each pair of input values, we're going to find the maximum of those. The maximum of those gets compared to the maximum. The minimum of those gets compared to the running minimum. It's O of n both ways, but we can actually reduce it to a lower number of comparisons, basically on the order of 1.5n rather than 2n. Now, this next one is going to be a bit tricky to see. What we're doing is we're looking at how do I categorize multidimensional data. So this can be used for x and y coordinates. It can be used for other things. So the idea is when we used a binary tree, our binary tree was actually a one-dimensional tree. We made our decisions on the same type of value every time. So I said, hey, I've got some letters, M is at the root of the tree, and therefore G should go to the left of it, T should go to the right of it, and then when I get to G, I say, well, where does A go? Well, A has to go to the left of G. This is a one-dimensional tree because I always make my decision based on that one value that's there. Well, what if there wasn't one value there? What if there were multiple values at each vertex? So what I'm going to do is I'm going to pick one of them to be the root, and then I'm going to partition all of the other values based on that on my first comparison and decide, okay, you all go left, the rest of you go right. Then when I get down to the next level, I'm going to do the same thing again. I'm going to pick someone to be the root of this subtree, but I'm going to use a different attribute. So I might do it, say, the first time I would base it on x coordinates. I'd say, okay, I've got an x coordinate. This one is in, I hope, in the middle. Everybody whose x is smaller goes left. Everybody whose x is larger goes right. But then at the second level, I'm going to pick somebody to be the root of this subtree on the left. But then I'm going to make my decisions on y. I'm going to say, okay, everyone with a smaller y goes left, everyone with a bigger y goes right. And we're going to build this tree. the same way we would build a binary tree, except each level we change our decision. So at one level I use X, next level I use Y. This, for example, with a two-dimensional tree. My first dimension would be X. I divide everybody left and right based on X. Then I recursively make a decision on Y. Then I recursively make a decision on X, etc. So here's an example of doing that. So what I've got is I've got a bunch of polygons here. And really what I've got is a bunch of points. What I'm interested in are these points. All right, so I'm going to look at those points, and every level of the tree, I'm going to make a cut based on X, then Y, then X, then Y, etc. And it would take more levels if I had more points. Okay, so I made my first cut on the points based on X, and I happened to choose 7, 2. So here 7, 2 represents, let me get rid of my markings. Okay, so 7, 2 right here represents that point there. I just happened to pick that one. So 7, 2 becomes the root of my tree. Everybody with a smaller x goes left. So that's these 3 points go left, and these 2 points go to the right subtree. Then once I get to this left subtree, I picked one of them, whatever one I encountered first. I happened to encounter 5, 4 first. Let me change colors. So 5, 4 here became the root of that left subtree. And then everybody that was supposed to be in here, this one and this one, get divided up left or right based on their y. So the one with a smaller y value, 2, 3, went to the left. The one with a larger y value went to the right, 4, 7. And we repeat this process over in the right subtree. 9, 6 happened to be the first one I saw. 9, 6 becomes the root. And then 8, 1 has to go to the left of it because it has a smaller y. Now, the neat thing about this is when I start to try to ask questions about other points, the KD tree can be used to help me make those decisions. So for example, if I want to say, hey, I've got some other point, 4, 4. I've got some other point, p equals 4, 4, and I want to know who is the closest actual point in my n. So I had n points over here, and I've got some other point that's not a part of that. So I've got my n points in my KD tree, and I've got some other point, and I say, hey, which point in your KD tree is the closest to the point that I've got? Now, if I didn't have the KD tree, I would have to check the distance against all of them. But with the KD tree, I can limit my search to the ones that are in a certain direction. So if I'm trying to find like the closest points to 4, 4, I could say, hey, let's do searches nearby that. So I'd say, okay, well, 4, 4, let's look at 7, 2. Okay, so 7, 2, 4, 4 would have to be to the left of that. Anything that's to the right of 7 is going to be further away from 4. So 4, 4, if anyone's close to 4, 4, it'd have to be either 7, 2 or someone to the left of it. Okay, we go to the left of that. 5, 4. Okay, now let's compare the two we just had. I've got 7, 2 and 5, 4. Which one is closer? Okay, 5, 4 is closer than 7, 2. If there's anyone closer than 5, 4, they would have to be near 5, 4. So now I make a decision based on y. Oh, look, these two have the same y coordinate. Well then, if there's anyone else, they've got to be nearby again, so we can repeat this search. We can also do, so that's one way to answer a certain question. What if I wanted to answer a different question? So now I've done, when answering this question, I've turned it from O of n into now O of log n. Now the construction took me longer. I had to insert the points. It's n log n. Oh wait, it's n log n. In the average case, if I don't end up with a big stick, could I do a multi-dimensional AVL tree? Ooh, that'd be harder. So we've got our construction of this. Took us O of n log n time, but now searches take log n time instead of O of n time. See, if I wanted to say, if I didn't have the KD tree, I'd have to take that point, compare it to all n of them. The KD tree has gotten me down to a log n search. It also, though, allows me to answer other questions. Suppose I want to know, I have 2 points. I have the point 3, 9, and I have the point 1, 5.5. Okay, let's look at where those are on the graph. So I've got 3, 9 would be about right here, and I've got the point 1, 5.5 would be right there. What I want to know is there anyone within the rectangle described by those 2 points? The KD tree can answer that for me. So there's an example of another use of the KD tree. So we can find closest point to a given point. We can find any points within a bounding box that we choose, etc. Another one. So here's a thing that is an easy idea, easy to do with physical materials, hard to do with code. So the idea is I've got a bunch of points, and I want to find the polygon that encloses all of those points. Now, if I stuck nails into a board, if I had them all there to begin with, if I had my points were represented as nails in a board, then all I have to do is O of 1 time, I stretch a rubber band around it and let go of the rubber band, and that one rubber band has found me all the points on the outside of the polygon. That is called the convex hull. It's all the points on the outside. So if I had all the nails there to begin with, it's O of 1 time. If I had to nail them in one at a time, that would be n nails, snap the rubber band, now it's O of n time. Now there are ways to do this in code with, we can do n points in n log n time. Physical universe is sometimes easier than the computational world. So there are ways to do this, and you can look them up if you want to. Basically, we pick a point, we sweep a line around in a circle, we look at polar coordinates, and we can find the polygon. If you're using MATLAB, they've got a built-in function. You give it a bunch of points, call the convex hull function, it tells you which points are on the outside. Polygonal operations, I'm going to skip over this one. This one's getting a little bit too complicated. This is the one I wanted to get to. So this is the last slide we're going to do, except for possibly the answer to this question and a summary. So if I gave you n points, and I want you to divide the remaining points into 2 halves. So I gave you a list of endpoints. I want you to find a line that crosses through 2 of the points that divides the remaining 1 into half. Now, we can make this a little bit easier. If I tell you there's an even number of points, then we don't end up with like 5 on one side and 6 on the other, so it will be half and half. Also, if I tell you up front that there's no 3 points that are collinear, because if there was, let's say there were 4 points, but 3 of them happen to be all on the same line, then I can't divide the remaining points in half. I can get close, but suppose I tell you those don't happen. There's never 3 on the same line, and there's an even number. Can you do this in O of n log n, O of n log n worst case time? I wasn't able to do this thinking about it. It took drawing it out to come up with the answer. Now, for those of you watching live, I'm going to give you a little bit of time to think this out, maybe draw it out on paper, and I'll come back to you in a minute. And then if you're watching it later, you can obviously pause and continue when you want to. So go ahead and talk to each other. You can go ahead and use the chat if you want to throw around ideas. Now that you've had some time to think about it, I'm going to give you a hint. This is an important question. Does the starting point matter or not? You've got a lot of great ideas, and I used some of them when I was working on this. It's actually not the KD trees. It's not applicable to this one. And if I had thought of that, I would have mentioned that up front. So a couple of things here that people mentioned. So Elang, finding the median X and Y. That was my first thought. And I realized, though, that that doesn't help you. It took me a while to get there. Daniel's point is true. The split doesn't really depend on finding the right set of points. If you pick a first point, there is a second point that divides it. So, I see when you're getting on the medians, median is the right track. So median is the right track, though, but it's not the initial points. So if I was to take any one of these points, let's say this one right here. If I take that point and then I go and I calculate for everybody else, what is the angle to that point? So what's the angle to this point? Then I calculate what's the angle to that point, what's the angle to this point, what's the angle to that point. If I get all of the angles, Then I just need the median angle. Whoever's the median angle must divide the angles. So if I've got 10 points here, if I get 9 angles, if there's 4 of them less than a given angle and 4 of them greater than a given angle, they've been divided. So the sorting is right, except we need to sort the angles. So if the key is that we've got to pick an arbitrary point, otherwise we're going to end up in n squared. Now the n log n time to sort them would get us the median. There's actually a slightly better way here. If we sort them, we will get it in n log n time guaranteed. If we produce the vector of angles, and then we do nth element. If we do nth element on that vector of angles, where we give it the middle index, nth element is actually O of n time average case. So this problem can be solved in O of n time average case if you use nth element. But it could still be, it still could be O of n log n in worst case, because it can degrade. But of course, Igor Markov, when Igor was teaching this class with me, he asked me this question while I was in the middle of editing the exam, when the exam didn't include this set of slides at all. So I'm like trying to edit slides and trying to improve the exam, and I'm working on like an AVL tree question while he's asking me about this one. So the summary here, and I've got one more thing after we talk about this. So we got the summary slide here of the different things that we can do with computational geometry, places it comes up, etc. The other thing I wanted to mention is the sample exam is online on Canvas. Actually, sample exams, plural, are online on Canvas. And we're also going to put them on, and they're in the files. So if you look at Canvas files, exams, or practice exams, it's in there. We're also going to put them on Canvas in quiz form so that you can see basically how we're going to be doing the actual exam. So the actual exam, the final exam, is going to be multiple choice questions that are on Canvas quiz. I mean, that's what Canvas calls it, is quiz. So the Canvas quiz, air quotes there around the word quiz, is going to be the multiple choice, and then the written ones you'll be able to turn in on Gradescope. You can turn it in by typing in the code. You can upload a scan, whatever it takes, kind of like the lab. Now for the review time, so that'll be Thursday. This week, Thursday, there is no lecture. We got done with stuff a little bit early, partly because some of the lecture videos we went a little bit over time just to finish each one each day. And this semester ended up with an extra day in it. It's odd. Some semesters have an extra day in the first half, some in the second half, some don't at all. So Thursday this week, there is no lecture. Get your project done, get the lab done, and then next week, Tuesday, will be the review lecture. So take care, everyone. I'll see you in Prof's hours if you need help on the project or the lab. Oh, one other thing on the lab, on Lab 10. On Lab 10, if you haven't noticed it yet, it's in there write-up somewhere. If your function just does a return -281 for the meals plan, the AutoGrader will give you a feedback help page, which you will see when you click on the timestamp and look at the output. There'll be a whole graphic there that will really help you visualize it. And also, another question that came up on Lab 10 today, people asking about it. One is, Lab 10 can be done either bottom up or top down. Doesn't matter. If you do it bottom up, then you would have like a double nested loop. If you do it top down, you will have a loop and a recursive call. And so, yeah, okay, so I'll answer a couple questions. So on the exam keys, yes, they will be posted. So like the PDFs with questions are already there. The PDFs with the answers are set to auto reveal at basically the end of next Tuesday. So the end of next Tuesday, the answers will be available in PDF form. On the Canvas quiz, I'm not sure if I'll make the answers available there or not. The PDF already got them. It's ready to go. And it's already set to auto reveal at like 7 o'clock a week from today. On the Canvas exam, it will be timed, and it will be timed from the starting point that you asked for. So we're going to give you, so if you asked for an 8 a.m., we're going to basically give you, we haven't gotten it like 100% decided yet, but our idea is we're going to give you like 7:50 to 10:10. So we'll let you start a little bit early, we'll let you end a little bit late, but really that's intended so that you can have your full 2 hours and get things submitted in the extra time. So if you sign up for 8 a.m., we're planning on like 7:50 to 10:10. If you signed up for the 4 p.m., it would be like 3:50 to 6:10. And yes, Rajiv. So just like the PDF, we're getting the PDF ready in quiz form on Canvas. But it will be, the Canvas part will be really like the labs you've been doing. So you're pretty familiar with it as it is. And then we'll also have, so we've already got the practice exams as PDF. We're working on getting those typed in, so we'll have the practice exam as a quiz, but you're already fairly familiar with that part of it. And then we'll also work on getting the practice exam writtens as a grade scope, so that it won't count as part of your grade, but it'll just be on grade scope so you can practice submitting. But that's going to be similar to how you've been doing the lab written portions. So the ways that we're doing it are ways that are familiar to you already. Right, and we're going to start like 10 minutes early and then 10 minutes late, so then you've got a little bit of delay before your next class, if you've got another exam that's doing one at 10 o'clock. But hopefully with our different time slots, people have been able to find one that they don't have 2 back-to-back exams, and also one that fits their time zone that they happen to be living in right now. So really, you'll have 20 minutes extra. That's not just including submitting. I mean, if you're confident in your, hey, I've already submitted the grade scope portion, fine, I've got an extra 10 minutes to use to work on my multiple choice questions. So you've got an extra 20 minutes as overhead for dealing with the format. But when you start the quiz, it'll actually have a timer on it, on the real exam. And what I might do is for the sample exams, I might do like one of them has unlimited time and the other one has limited time, and so that way you can see it. So for the practice exams, I will, that's a good idea. I'll talk to the other staff and faculty about that. I might make the sample exams, one of them be timed, just so you can see how it works. You're welcome. Yes, we decided we were being too unreasonable about that. Sometimes we make decisions and then we realize we are allowed to be nicer than we were planning to be. For the no. Once on the Canvas quiz, the exam, once you hit submit, that's it. But you can leave your browser open until it's about to close, and If you don't hit the submit button, it will submit for you when your time runs out. So you will only have one submission, because if we allowed you unlimited submissions, then you just go, hey, I've chosen my best answers for these 4. I don't think they're right, but I'll just submit these, 4 times 5. I'll submit them 20 times. Ha, perfect score. So no, on the exam, you get one submission, but it will be set to auto-submit when time runs out on you. So like I said, Pratik, I'll set up the practice exams on Canvas so that you can see one of them in the real format with limited time, only one submission, etc. So I'll make one of them like you're used to seeing, where you have unlimited time, etc., and I'll make the other one like the real one. So what I would recommend in the next week, besides obviously getting the project and the lab done, is start looking at the PDF. Start going through the questions. In fact, what one student said they like about having 2 exams is they can use one exam as an, hey, this is my getting ready exam, just seeing what types of questions are on it and helping me study and helping me get my cheat sheet ready. And then I'm going to use the other one as the, hey, this is the one I'm taking, as if it's an exam. And then on the idea of cheat sheet, even though you can use whatever you want during the exam, since you're going to be at home, I would still recommend a cheat sheet as good, because it's got the things that you think are most important all in one place. So rather than going, oh, wait, I got to go to the lecture 20 PDF. Oh, wait, I got to go to the lecture 18 PDF. Put the stuff that you know you're going to need, that you're going to want to look at right in front of you. On a cheat sheet, digital or handwritten. Handwritten is better. The more time you spend handwriting it, the less you need it. So it looks like we're running out of questions here. I'll wait for a little bit more and see if we have any other questions you'd like me to answer. Otherwise, we're done for today.